This is section 1.1, part A, functions. Your I can statements for this section. I can describe subsets of real numbers, and I can identify and evaluate functions and state their domains. So when we talk about real numbers, there's a bunch of subsets inside real numbers. Real numbers just mean that they exist, and we represent real numbers with that R. The first set inside is rational numbers. Those are numbers that can be written as decimals that end, repeating decimals, or fractions. Then we have irrational numbers. Those are numbers that have decimals that do not repeat and have no ending point. Integers are values that do not have decimals, but can be positive or negative. Whole numbers are the integers that are 0 and positive, and the natural numbers are just the positive integers. So there are two different types of ways we can write about sets of values. The first way is set builder notation. This is an expression that describes a set of numbers by using the properties of the numbers in the set to define the set. So this is an example of set builder notation. We're talking about the variable x. This vertical line means such that. So we're talking about x such that x is less than or equal to 6. And over here on the right side, it tells you where x is located in which set of numbers. And it says x is an element of the real numbers. So we're talking about all values of x where x is less than or equal to 6 in the real number set. So if we're going to describe each set in set builder notation, on the first one, if you notice, those are values that are 8 or greater. And they are not all the numbers, they are only the integers. So x is just going to be contained inside the integers. So if we write A in set builder notation, we're going to say x such that x is greater than or equal to 8, and x is contained in the integers. And we use the z to represent integers. On the second set, we just want all the values where x is less than 7. Since it's not listing out the values, that means it could be any number, which is the real numbers, which we represent with the R. If they give it to you in this form, you already have the middle part of your set builder notation. So we can just say the set such that x is less than 7, where x is contained, or x is an element of the real numbers. So again, that is x such that x is less than 7, where x is an element of the real numbers. On part C, we're talking about all the multiples of 3. So that would be 3, 6, 9, 12, all of those numbers going up. If you notice, all of those numbers are integers, so they will be contained in the element will be contained in the integers. But we're going to have x such that it is a multiple of 3. So we're going to say x such that x is equal to 3 times n. And in this case, we're not going to talk about where x is located. We're going to talk about what group of numbers that n is located. And n is going to have to be located in the integers. So for this set builder notation, we have x such that x is equal to 3n, where n is an element of the integers. Now we also have interval notation. This is an expression that uses inequalities to describe subsets of real numbers. If we have greater than or equal to, less than or equal to, or just equal to, we're going to use those square brackets. If it is not equal to, we use the curly brackets. When you're going off to positive infinity or negative infinity, we do use those curly brackets as well. So if we write these in interval notation, if you take a look at part A, it says x is between negative 8 and 16. That negative 8 is not equal to, so that'll be a curly bracket. The 16 is equal to, so that will be a square bracket. So if we look, we're at the left side, it is not equal to. We have that curly bracket. On the right side, it is equal to, so we have a square bracket. If we do back up for a second, when we're looking at these sets, there are two symbols that you can see. The first symbol means and. I can turn that into a capital A if I needed to remind myself that it is and. And the second one stands for or when we're dealing with sets. So if we look at the second set, we're looking for all the values of x, so they are less than 11. So it does not equal 11, so it will be a curly bracket. Everything to the left of that would be taking us down to negative infinity. So our interval notation would look like this. Remember, anytime you have an infinity, it is always going to be a curly bracket, not a square bracket. And again, that 11 is curly because it is not equal to. On part C, we have two different sets. There's an or in the middle of it. Our first interval is going to be less than or equal to negative 16. It has that equal to part, so it is going to be a square bracket. And then we also have the part where x is greater than 5. We're going to have to use that symbol for or in between the two intervals. So we want less than negative 16. Less than means to the left, so we're going towards negative infinity. And then it goes up to a negative 16, including that negative 16, so it is a square bracket. Or, we use that or symbol, 5 and up, but you want it to not include 5 because it's not equal to, so it is a curly bracket. A function is a special type of relation where each input is assigned to only one output. So when we check these, for every x value, there can only be one y value. So if x is 1, y is 3, we cannot have one where x is 1 and y is negative 4. For each x, there can only be one y. One way to check to see if you have a function is to do the vertical line test. So if you graph your points or graph your line, whatever information you have, if you can draw a vertical line and it only touches that graph in one place for every vertical line, then it is a function. So we're going to determine if each statement or each graph represents a y as a function of x. So if the input value of x is the student's ID number and the output value y is the student's score in a physics exam. Each student ID number is assigned to only one student, and each student will only have one score on their physics exam. So that would be a function because for every x, the student ID, there is only one y value, the exam grade. If we take a look at this, we first need to get the y value by itself. So we're going to solve for y. To solve for y, we're first going to take that 2x to the other side. Right now it's negative, so to move it, we're going to add it. Next, we need to get the y by itself. Right now it's y squared. Opposite of square is to take the square root. Remember, when you take the square root, there is a positive and negative value. So if you take the square root of both sides, we're going to end up with y is equal to plus or minus 2x plus 5. Since we do have that plus or minus, that means for each x value, there are two different y values that we could get. So this would not be a function. If they give you the information as a table, you just have to look and see if any of your x's repeat. If all of the x's are distinct values, none of them repeat, and they each have just one y value, then that will be a function. So for this table, none of the x's repeat, so this is a function. If we take a look at a graph, if you draw that vertical line, you can see that that red line touches the graph in two different places. So therefore, this is not a function.